Okay, so for the 4 of you that have chosen to stay, today we'll continue context-free grammars. So to recall, last time we looked at fooling sets. The idea was we have a class of languages that are regular languages. They can be expressed through regular expressions, DFAs or NFAs. When we try to represent a language that is not regular, for example, canonically, some examples that we have seen so far are the language 0 to the n, 1 to the n, for n greater than or equal to 0. We've seen the language WWR, where WR is the reversal of a string in a language. We've seen languages that are irregular. The idea was, okay, why are they irregular? Because if I wanted to build a DFA for it, I would need an infinite number of states, but the machine needs to be finite, therefore it's not regular. So today, we'll look at a problem. Let's look at the following problem. I want to build a context-free grammar for the language. L equals 0 to the I, 1 to the j, 2 to the k, such that I equals j or j equals k. You're given this language and asked to classify it. Okay. Since this is on context-free grammars, we kind of know it's irregular already. But let's say I was asked to prove. I know it's irregular intuitively because I'm doing some sort of counting. If this, okay. Here's another way to know it's irregular. So this is my mystery language, and I don't know if it's regular or irregular. There are several ways of proving that this is irregular. 1, use a fooling set. I can do that by constructing any arbitrary number of fooling sets. 2, if you take the intersection with this language, it ends up being this language, which is irregular. So many ways to prove it's irregular. Next, we ask you, is it context-free or not context-free? Okay, so in order for, by the way, have we taught you how to prove a language is not context-free? So what should you always circle? Think about that. When you see this, if you see this. Okay, so this language is context-free. How do we prove it? A couple of ways. We can either give a set of production rules, or we can build a push-down automata. So I'm not going to give formal definitions of what these things are. I will just show you. A production rule, essentially, is a big character, a squiggly line, a small character, and some other big and small characters. Let's say I put the letter A here, okay? And this is a 0, or this is an epsilon. What this essentially means, actually I'll just put an S here. What this means is, you can think about this word as generates. These are basically our ors from regular expressions. This means starting at S, I can generate the string AS, or 0, or epsilon. Okay, so let's say I start at S, and then from it, I replace it with, or I generate the string AS. Okay, now I have a character in a string that's A. Let's say I generate epsilon from here. So I take the string and I generate epsilon. What I'm left with is the string A epsilon or AE. Alternatively, S can just make 0, or S can make the empty string. So can someone describe the language produced by this context-free grammar to me? I've given you this set of production rules. You don't know anything about grammars. All you know is that this arrow means you can replace this symbol with this one. What is the language described by this context-free grammar? Okay, we'll start by listing strings in the language and not in the language. 0 is in the language, epsilon is in the language. Is the character A in the language? Yes. How? Because I can take AS, so I can take AS, and then choose to replace this S with an epsilon. So character A is in the language. Okay. Can someone give me a string of length 2 that's in the language? AA. Skipped my meeting yesterday. Okay. So yes, AA is in the language by the same logic. I can make A. So I would start with S. I replace it with AS. And then I replace this with another AS. This character stays the same. And I get AAS. And then S gets replaced with epsilon. Okay, cool. So AAS. What else? I can have AAAAA. And then the last character could be 0 instead of epsilon. So what do we see here? We see strings that, yeah, someone should be able to describe this language now. We've gone through enough strings. A star, brackets, 0 plus epsilon. Yep. And then I don't need epsilon because, yeah, I do need epsilon. Cool. Yes, I think that works. So you can not pick A, you can pick a 0. So this is a regular language. This is what this context-free grammar represents. So again, production rules, add a character, move to a new letter, or. Characters that starts with A, and you can see that from the recurrence, like characters that start with A, and you can replace them as many times as you want, or end in 0 or epsilon. So this is important, because now I'm going to ask you to write a set of rules that look like this, and then you'll also need to write a set of rules that look like this over here. So okay, I proved it's irregular with a fooling set. Now I want to generate a context-free grammar. So let's see. I want the number of i's to equal to the number of j's. How can I do that? Or I want the number of j's to equal to the number of k's. Let's pretend the alphabet didn't even have 2 right now. And there's no restrictions on I, j, and k, so they can be 0. Let's look at the language. Let's first make strings where the number of zeros is equal. Yeah, the number of zeros is equal to the number of ones. So let's break it down. Can someone give me a context-free grammar? I start at S. How can I make the number of zeros equal to the number of ones? What is a grammar that'll do that? So I need to put something here. Okay, what's the smallest string that has the number of zeros and so yes, what could I replace this with? You with your hand up. Or epsilon. Yes, right? So intuition here, somebody else has already given me a string in the language with an equal number of zeros and ones. What I can do is add a 0 to the left and add a 1 to the right, and I still have an equal number of zeros and ones. Okay, so that's this case. So let's call this, this is 0, 1. So I'll call this actually P for prefix, and you'll see why later. Okay, now I want to generate the same language where j equals k. So number of ones equal to the number of twos. One P, one P. No, it respects ordering. Number of ones, like I meant to say number of zeros equals number of ones and respects the order of this. Yeah. If it was truly just equality, then you're right. Okay, so now I want the number of ones equal to the number of twos. I'm just going to copy this grammar as is. So this is going to be, I'll call this T for twos, and then I'll put 1T2 or epsilon, capital T, okay? Cool. So now I can make these equal, and then I can make these equal. So now I have 2 sublanguages. Okay. Let's say, so now I can generate equal zeros and 1 prefixes, and I can generate 1, 2 suffixes that are right. So I can generate things like do. This would be generated, and I can make things like, I need to merge them so that I can get a proper language out of this. So what do? In this case, what's missing from the end of this thing? So I have, if I assert that the number of zeros and ones are equal, I can put any number of 2's at the end. So I want in my head some sort of additional supplemental rule that allows me to basically take P and append 2 star to it. Okay. What's missing here? This generates suffixes, but I need some sort of rule that will allow me to generate an infinite number of zeros first, and then put the character T after. So then let's just build these two languages. We'll call this one, I can't come up with names. Oh, I'll just use alphabets. Okay, hey. So what is a context-free grammar for the language 2 star that starts at A? So, did you say something?
2A or epsilon.
Great. A goes to 2A or epsilon, and there should be an arrow. Okay, and that handles this. And then for 0 star, I do the same thing. B goes to 0B or epsilon. And now I can put everything together. I have something that generates an equal number of 0's and 1's and adds unlimited 2 to the ends. I have something that generates an equal number of 1's and 2's, and I have something that will generate all the zeros I need in front. Yeah.
Yes.
What do you want me to do?
The 2's are on the right side.
Oh, I didn't mean to put P here anyways. Right now, I'm just trying to get...
Yeah, you append 2's to the right.
It doesn't matter. Here's why. So let's say, so the question is, S leads to 2A, or 2S epsilon, versus S leads to S2 epsilon. I want to generate, this is basic, both of these are the language 2 star, is what we're trying to represent. I start with 2S, I replace S with 2. So I with 2S. I replace this with epsilon. Okay, from this one, I start with S, and I replace it with S2, and then I replace this with another S2, carrying this downward. And then I replace this S with an epsilon, and I get the same thing. So essentially, what this distinguishes is, am I going to start generating things from the prefix and continue adding suffixes to the end? Or am I going to start with the end of the string and start adding prefixes to the string? In this specific case, it doesn't matter. Does that clear that up? Cool. Now, this won't always be the case, but just for this language. Okay, so equal numbers of 0's and 1's, that's given to me by P. 2 star is given to me by A. So I concatenate these two languages together. Or equal number of 1's and 2's are given by T. And then the infinite prefixes of 0's or no 0's are given by B. And then this is my starting state. And yeah, that's my grammar. So if I was writing a final solution, I would take, I have my S here, I would just define things probably a bit better. 0p, 0p1 or epsilon. A will lead to 2a1 or epsilon, 2, 1 or epsilon. What's going on here? T goes to 1, T2 or epsilon, and then B goes to 0, B or epsilon. And this would be my context-free grammar. Questions? Also, this is clearly not the most compact way to write this. A lot of these rules can be collapsed into each other. But the reason I did it this way is because I think it's important to get an intuition about why the grammars look the way they do. And in the solution, sometimes you'll see like one really long line of S, and then it's completely uninterpretable. Does this make sense? Okay. Let's go to another example. Okay, what is it that we want? We'll do problem 5. We want the language 0 to the I, 1 to the j, 2 to the I plus j. For all ij bigger than or equal to 0. I have an idea, but I'll just write it here for now so I don't forget. Okay, so we want to write a context. Is this regular or irregular? We go through the motions and we're like, okay, I think it's irregular. I think it's irregular because this needs to know how much stuff I've put here before. It looks like I need a counter. I can make a fooling set, easily construct it, blah, blah, blah. Okay, so we'll skip the fooling set exercise for now, although it should be pretty straightforward. Let's go straight into the context-free grammar portion of this. I want to generate a set of production rules. So again, when you have multiple characters in the alphabet, try taking one out. I'm gonna cover up this 0 here. If let's say I force j equal to 0 right now. So force j equals 0. Then you have the language, what? 0 to the I, 2 to the j. Oh no, 2 to the I, right? If j is 0, this becomes 2 to the I. For all ij bigger than or equal to 0. This looks exactly like 0 to the n, 1 to the n, which we've written so many times before. So this one I forced j to be 0. I'm now going to force I to be 0. So let's force I to be 0. Okay, if I force I to be 0, I get 1 to the j, 2 to the j. For all j bigger than or equal to 0. Do we know how to write context-free grammars for these two? Yes, we've done it 100 times. So S becomes, yeah, okay, let's call this, I'll just stick with A. So A becomes, someone should tell me what to put here. I'll turn around this time too. How do I write this as a context-free grammar? Are there no ideas, or is it too trivial of a question? Yeah.
Is it 0, A2, epsilon?
Yeah, I think so. Yeah, that works. So that goes to 0, A2, or epsilon. And then by analogy, we'll do the same exact thing down here. 1, B, 2, or epsilon. Okay, cool.
IJ greater than 2.
No. So I've broken it down into two languages. So if I can make this, what's missing is for me to put an unlimited amount of j's in between. If I can make this, what's missing is for me to, not an unlimited, but the right amount of j's in between. So we have these two sub-languages that are similar-ish to what we want to do. The good thing here is, let's say I want to insert a 1. So I have this 0-2 paradigm. If I want to insert a 1, I can insert a 1 on both sides. Okay. So this language doesn't have 1s. So this would give me a string something like, for now, 0, 0, 0, 2, 2, 2. I want to insert a 1 into the language to make this language correct. Where do I put the 1, and what else do I need to add? So the goal is to insert the character 1, so this is a valid string. Yeah. Go ahead. Where would I put the 1? If you were raising your hand. Oh, okay. In the middle, great. And then I would have to add a 2 here. Okay. If I wanted another 1, I would have to put the 1 here and add a 2 here. So let's insert a breaking point here that allows us to do that. So let's say, let's take, yeah. So let's combine these sort of two definitions together. And every time I insert a 0, add a 2 on. Every time I insert a 1, add a 2 on. So every time I insert a 0, add a 2 on, and that can go here. And this can be one of my languages. And then, and we'll call this B. Anytime I insert a 1, add a 2 on to the end as well. So, let's see. B goes to 0. First I set this one to be 0. Okay, yeah, that's what I did. So I set this to be 0, and then I got, this is a 1. Okay, cool. So 1, 2B. So if I start here, if I take this language, this generates suffixes of the strings. So I have this thing that generates, this might be an easier way to look at it. So I have the string 111, 222. If I want to insert a 0 and keep it into the language, then if I inserted a 0, I need to put a 0 here and a 2 here. So you can think about that as the middle of the string. And what I can do is say, hey, okay, now I'm going to wrap this in this definition. So it would be as if I took this B and put it here instead. So this 1, 2 thing can get wrapped in the 0, 2 thing. So to allow myself to do that, I will allow myself B to be replaced with a string from the language A or epsilon. No, it should be the other way around, yes. Thank you. So what should I put here? I should allow this to be replaced from a string in the language B or epsilon, yes. Now, I should be, oh my God, the 1s and 2s look awful. Let me make this clear so that there's not a lot. Can you guys tell now which ones are 1s and which ones are, okay, cool. I've wrapped this now in, this A can get replaced with a B, so let's just start randomly. We take 0A2, I replace this A with 0A2, and drop the rest of the characters down. I replace this A with 0A2, drop the rest of the characters down. Okay, then I decide, you know what, this time I'm going to replace the A with a B. I could end it here and get a valid string, or I'm going to replace the A with a B, and then I get 0, I replace it with 1, 2B, and then I get 0, 0, 0, 1, 2B. Oh, sorry, no, 1B2, 1B2. Yes, and then 2, 2, 2. Now this 1 accounts for here. Then in the next step, I choose to replace this with an epsilon, and I should be good. 4 characters here, 4 characters here, 0s come before. Does this make sense? So now I always need to start in a start state. So my starting options are, I'm allowed to skip the, what is it? Yeah, I could go to A or B. Cool. Questions? So the reason why I wanted to remove a character was more for demonstration. It was to show that you can think about this as nesting a language in between 2 other languages. In the same way, we have 0 to the n, 1 to the n. If I want 0 to the n, some other language, 1 to the n, just throw that in between if it doesn't depend on n's. Yeah.
Like in the midterm, if they ask you for a start state.
Yeah, the start state leads to A and B. Can you have a DFA with? Can you have an NFA with multiple start states? Let's ask that. But you can fake it by making a single start state and epsilon transitioning to all the other ones, right? Yeah. Okay. I'll move on if there's no questions about this. Good? Okay. Cool. Let's now look at PDAs. So our issue with, for example, the language 0 to the n, 1 to the, oh, okay, actually, no. I had an idea here. I wrote idea 64. Let's address that. Let's say I wanted to make it such that I want to add a restriction here such that the let's see, 2 times I plus j is greater than or equal to 64. Let me ask, is this language regular, irregular, or context-free? Or context-sensitive? So I've taken the problem they've given you and made a slight modification to it where I'm saying, now I want to add the restriction that 2i plus 2j is bigger than 64. What does that tell me about the minimum possible length string accepted by this language? Sorry? 32. It's 64. So where I got 2i plus j from was 1, I pulled it out of my ass, and then 2. If you sum these, you get 2i plus 2j. So I was trying to restrict the length of the languages in the string to be bigger than 64. So if I only want to generate things bigger than 64, would the language still be context-free? I just need 64, like all possible 64 valid strings that you could generate before. And we could do that, yeah. So you need all possible valids. Yeah, go ahead. No, it is context-free. I'm not asking you for a grammar. I'm asking it if it is context-free. If you wanted to represent it, what you would essentially do is you'd add on all valid 64 length strings, because we probably, let's make it greater so my life is easy. Yeah, greater than or equal to, yeah, strings. Right, so that are, yeah, sorry, that are less than or equal to, no, yeah. Sorry, what was your question? How would you represent the grammar? You would need to redefine your base cases for A and B to be the valid 64 length strings in this format. And then instead of epsilon being your base case would be all the possible length strings of length 62 that would fit here. Or all the possible strings of length 62 that would fit here. Does that make sense? If I had made it bigger than or equal to 2, this already, if I make it bigger than or equal to 2, I remove the epsilon, right? Push it to the limits. Let's say I said bigger than or equal to 2. The only way for this to be equal to 2 is if less than or equal to 2 is if this is 0. So if I wanted at least odd length strings, I would remove epsilon and replace with another character. So I'm not going to dwell on that too much, but it was a thought exercise. 2, important. So this is idea number 1. I've said, hey, I want strings bigger than this fixed constant, still context free. Now 2, let's say I had said 2i plus j is actually now less than or equal to 64. So this same language, but I add this restriction in here. Is the language regular, irregular, or context free? Does everyone understand the restriction I'm putting? I'm saying all strings of this form, but the length has to be less than or equal to 64. Yes, why? You can use a finite state machine, and also if you think about it, okay, if my language is finite, I can literally make a regex that is the OR of all of those finite strings. So that's another thing you should know. Every single finite language is regular. So I don't know if this is a lemma, but I can just write lemma. Every finite size language is regular. So if I give you a language that looks irregular, and then I put a length bound on it that makes it finite, the language becomes irregular. And this also works with, let's say, you have something like the language L equal to 0 to the n, 1 to the n. But then I say that n is bounded by 0 and 9,999. And then I ask you to ask, is this regular or irregular? Well, it's regular because it's finite. The reason you don't want to be writing a regular expression for this. So you just say, hey, any finite length language is regular. So irregular languages with that add restrictions that make the length of the strings in the language bounded and the size of the set bounded are regular. Anyways, back to this. We will look at this problem of building a push-down automata for let's see. Let's pick a language. What's a good one? Okay, cool. So we'll take the language L, where W belongs to, W is a palindrome. And W belongs to sigma star. So let's write out the context-free grammar for this before we build out the push-down automata, before we actually make the automata. So we say, okay, W is a palindrome. That means that if I have a string that's already a palindrome, some random string that's I can take any character from the alphabet, put it here, any character from the alphabet, put it here, and this final string is still a palindrome. So this would be C00, C, still a palindrome. Okay, so we see these buckets, and then we saw over here somewhere, we have lines, and these things are buckets. So now let's just do that in reverse. So suppose somebody already gave me a string that's in the language that's a palindrome. I can either add zeros to both sides, or I could add ones to both sides. We'll use y0, or 1, y1, or epsilon. And then we'll call this thing y, I guess. Y is a character. I should be proper about this. Okay, there. Cool. So we get 0 or 1. So this is a context-free grammar that represents palindromes. Is there an issue with this definition, though? So I'm asking for all strings that are read the same for, yeah, go ahead. If you had your hand up. Exactly, so what do I need to do to be able to generate odd palindromes? Great. Now the language definition is complete. Cool, now I want to build a PDA that does this. So if I were to actually ask you to write code to determine if a string was a palindrome, you would probably start with 2 pointers, one on the left or right, see if the characters agree, stop when you hit a midpoint. Another way of doing it is you have a stack. So you have string ABCD, or AAB, AB. You push AA, B, AA onto the stack. This is what you see. And then you pop it off of the stack. So you go AA, B, AA in reverse order. And then if these two strings are equal, you know the string was a palindrome. Another way of doing this, if you had access to a stack, so push the whole string on, pop it off. Are the strings equal? Yes, because the stack reverses the string. Another way of looking at this problem is you have a stack, and you have the string AAB, or we'll just say ABA. You say, hey, I'm going to push half the string onto the stack. So I'm going to push up until here onto the stack. Okay. Now I've finished my midpoint character. So I'm actually not going to push the midpoint character, let's say. I'll pop this off, and if the stack is empty, then I know I have a palindrome. So a more concrete example, C, D, C, 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 D. Okay. So I push C on, I'm at my middle character D, which I ignore. I pop C off, Stack is empty, palindrome. I get rid of the character D, and I just go C, 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 C. I go to my halfway point, and then I pop it off. Pop this off, my stack is empty. So the idea too is push half the string onto the stack. And check if stack empty. So counters may have been helpful, but DFAs don't have counters. NFAs don't have counters. DFAs, as we said, we're putting a limit, because they're not regular, we cannot build a machine that uses, yeah, go ahead. Does this not work? Bingo. So that's the question. How do you know? Know where the middle is. The issue with the first one in terms of a DFA is I don't have infinite memory. I don't know how long the string is, and I can only consume the string once. I can't go backwards, right? In this case, how do I know where the middle of the string is? Well, what do NFAs have that DFAs don't? What transition do they have? Great, so we guess. So we guess where the middle is. The midpoint. If you make a wrong guess for the midpoint of the string, either the stack character that you pop and the character that you have left will have left to read will not equal, or there will be characters left on the stack by the end. Yeah. No, the space complexity here, you're thinking about in terms of computer memory, is the space complexity is here equal to the length of the string, right, to some degree? With PDAs, and we still are not bounding our complexity by the length of the string or the length of the input. We're bounding our complexity by the number of states, the number of transitions, all of that. So let's say we have this machine that has a stack. So I add a stack here. We define these PDAs as follows. We have a start state as usual. Essentially, if you're traversing through the string, you have three operations. So if I get a string 0, 0, 1, 1, 0, 0, I read a character. So I read a character. I can pop something off the stack. And then I can push something onto the stack. Okay? So let's initialize the stack with a $sign to make it empty. So before reading anything, I'm going to put a $sign onto the stack. So I read the character epsilon, I pop nothing off of the stack, and then I put a $sign onto the stack. So again, read, pop, push. Is it read, push, pop, or read, pop, push? I don't know. Either notation is fine. Okay, great. What is it?
Read pop.
Good. Cool. So then, okay, I want to push half my characters onto the thing. So I say, okay, what I'm going to do is if I see a character, the first character is 0 or the first character is 1, I'm going to read it. I'm going to push that character onto the stack. So I'll make it explicit here. I read a 0, I pop nothing, and then I push the character onto the stack. So I put a 0 here. If I see a 1, I do the same thing. So now, if I have my string 0, 0, 1, 1, 0, 0, I've pushed, we don't know we're at the halfway point, but let's just say we are. I have to make a guess that this is the halfway point of my string and jump down here. So let's take a look. So I jump down to this state. In this state, what do? I have to pop the existing character off the stack. So I have some character, yeah, I make a guess. So this thing is basically saying, hey, I'm going to non-deterministically make a guess now that I'm halfway through the string. Epsilon or epsilon, read nothing, pop nothing, push nothing. Okay, I'm making my guess that I'm at the halfway point of my string. Now, I need to try to pop this part I've pushed onto the stack. Whatever character is on the stack right now, which will be 0, 0, 1, I need to pop the character that I'm reading off of the stack. So if I read a 1, I need to pop a 1 off the stack and push nothing. If I read a 0, I need to pop a 0 off the stack and push nothing. So let's go back to the case. How do we know the memory constraint that he talked about till the end? I push the string 0, 0. I'll put the string 0, 1, 1. This is non-determinism, so the guess could happen at any point. If, let's say, because, I consume a first character and I go here. Let's say I'm in this state and I have pushed 0 onto the stack. And I say, hey, this is my guess for the midpoint. Well, it says read a 1 from the input string and pop a 1 off the stack. There is no 1 on the stack. It fails. Let's say I make the guess here instead. I'm like, okay, read a 0, push it onto the stack. Read a 1, push it onto the stack. Okay, I'm non-deterministically guessing I'm halfway through the string. So I pop a 1 off the stack. But oh no, my stack's not empty. It still has a 0 remaining. What's up? you have a question? No? Okay, cool. So once I've exhausted everything, then when I see a $sign, I consume nothing from the input string, I take my $sign, I pop it off of the stack and push nothing here. This ends up being my accepting state. There's one more condition. When does this PDA fail? Now I have 3 circles. When does this PDA fail? So it makes the right guess for the midpoint. What happens on odd length strings? This is a palindrome, but if I guess that the midpoint is here, I will have 0 on the stack and won't be able to pop the 1 off. So I need a free pass, or a free guess, that basically says, if I see a 0 from my character, allow me to not touch the stack and go here. If I see a 1, allow me to not touch the stack and go here. And then I'm guaranteed acceptance. So back to his point, the memory we use, apart from the input string given, is just the number of states here. And at any point, since we can only consume the string once, the stack itself is somewhat bounded by half the input length, plus 2 characters. Does anybody have questions about the construction of this? Sorry? Yes, I do need a self loop on the second state to push more characters. Okay, so a couple of things can happen. Remember in an NFA I said, if you consume the entire string and you're not in an accepting state, then you reject. If you get to an accepting state, but can't transition out of it, but you haven't consumed the rest of the string yet, you reject. Here, if you get to the end of the string, but the stack isn't empty, you reject. Or you're not able to pop a character off of the stack, you reject. So acceptance is basically, have I been able to consume the string in one of these non-deterministic paths? Questions? Yeah.
Why is there a 1 and then an arrow? Isn't it 1 comma and then an arrow?
Where?
Is that a mistake?
The arrow that you drew onto the
Going
second
down.
state going down.
Yeah, that's a mistake.
I didn't know if
That was a mistake, yes. 1, yeah, read it 1, pop nothing, push nothing. Sorry, yeah. Cool. Okay, then we are good for today.